Hi, in this video we're going to look at using vectors to solve displacement and velocity problems. We're going to run the video the same way as we did the last one, so I've got 3 questions down here on the whiteboard which match with the questions on the associated worksheet, which you can find in the description. I'm just going to work through these questions. You can look at the timestamp to get the question that you like. Okay, let's get started. So, question 1. Particle A moves at constant velocity, v equals 512 meters per second. Particle B moves from the same point 10 seconds later at a constant speed of 15 meters per second. Determine at what time and location the 2 particles will meet. So we've got particle A and B at the same point. Particle A goes off. Sometime later, particle B goes and it eventually catches with particle A. We want to know how long that takes to catch and at what location it is. So what displacement they've moved. Now, because they both start and end in the same spot in terms of what we're looking at, we know that the displacement of A equals the displacement of B. And this is the equation that we're trying to solve. We also know that the velocity equals displacement over time. So these are our 2 big equations for this question. Our velocity of A is 512 meters per second. The velocity of B, we know it's heading in the same direction, but we're some scalar multiplication of that. It should be going a bit faster if particle B is to catch particle A, but this is what we know. We also know that the speed of B is 15 meters per second. Okay, so there's a few ways that we can look at doing this. The first way is to look at velocity A, and let's work out the unit velocity. So the vector pointing in that direction, 512, but that's only going 1 kilometer per hour. 1 meter per second, sorry. If we can find that, we can simply multiply that by 15 meters per second, or multiply it by 15, and we'll have 15 meters per second in that direction. So we want the unit vector of VA. So we need to find the magnitude of VA. Okay, that's 13 meters per second. So the velocity of A, if we wanted to find that unit vector, it is just our velocity of A divided by the magnitude. Okay, so this is going 1 meter per second in the direction of A. Now, if I want to find velocity of B, I know it's going 15 meters per second, so I can just say it's 15 on 13 meters per second. And that's how I can find the velocity of B. Another way I could do it is I could say that we know that the speed of B is the same as the magnitude of the velocity. So I could say the magnitude of VB equals, if I multiply this in, we will have 5K, 12K. So I can say this is my magnitude, or which is the same as my speed of B. I know that's equal to 15. So we've got 169k squared, square root equals 15. K equals 15 on 13. Okay, which we can substitute back into our original equation up here. and we get 15 on 13, 512 meters per second. So you can see we get the same answer both ways, just slightly different ways of viewing it. Okay, so we've got the velocity of A and the velocity of B. We want to work out what time they both meet. At that point, the displacement of A will equal the displacement of B. So if we've got SA equal SB, and I'm putting my underlines under there for my vectors, we're not talking about speeds here. We know this equation holds true, so we've got the velocity times the time of A equals the velocity of B times the time of B. Velocity of A is just 512 times the time equals, so that's the velocity of B. Now the time that B travels, if we go back up to our question, it leaves the same point 10 seconds later. So if A is traveling for t seconds, then this will travel for t minus 10 seconds. We can make this look a bit nicer. 15 t minus 10 on 13 by 512. Now because these vectors are the same, and the left-hand side equals the right-hand side, that means that t must equal, and we can solve for t. So we get our value for t is 75 seconds. We can work out our displacement. So our displacement is just 5 on 12 times t, and that's where they, 512t, that's when they'll meet. I could work out SA or SB, it doesn't matter, they're both the same at that point. By 75, and we will get an answer. So what's that, 350, 375, and that is the location in meters, because we have a meters per second here, times a second, cancel out, and we get a meters, and this is the location where they meet. So they meet at 375,900 after 75 seconds. And that is question 1 completed. Okay, question 2. Particle A moves at constant velocity 815. That should be meters per second. Particle B leaves this from the same point at the same time and direction, but at double the speed. Okay, so we've got A, it's going off at 815 meters per second. We've got B, it's heading off the same point, the same time, and the same direction, but it's going double the speed. So we've got 2 lots of 815, and that's B. This is A. Okay. Determine how long it takes until they are 350 meters apart. Okay, so this is a distance. So if we're working distance, we can work with this equation, speed equals distance on time. So far we've been working in velocity equals displacement over time, but we're just after a distance, so we don't need to keep all of our directions intact here. So let's work out what the velocity of A is. Velocity of A is 815. Sorry, let's work out what the speed is. Speed of A is just the magnitude of the velocity. So we get 17 meters per second. That means the speed of B is 17 times 2, 34 meters per second. We want to know when they're 350 meters apart. So that would be dB minus dA equals 350. Okay. So we've got distance equals speed times time. SB TB minus SATA 350. Now the time of A and the time of B are exactly the same because they're leaving at the same point in time. And we get 20.59 seconds. So after 20.59 seconds, particle A and particle B will be 350 meters apart. So in this example, because we realized that we were talking about a distance and that's all they were after, we didn't need to preserve the directions. We could break the problem down into a speed equals distance over time problem. So that's question 2. Okay, question 3. A particle starts moving from the point O with a constant velocity of VA equals 3 minus 4J meters per second. At the same time, a second particle starts moving at constant velocity from point B, where OB, the vector OB is 15I. Determine that, given that the two particles meet at right angles, determine the position vector OP where they meet, the velocity of the second particle. So when we're doing questions, first step is always to draw a diagram when you have something visual like this with different angles. However, you need to know what you're drawing the diagram of. Am I drawing the diagram of velocities, displacements? What is it? Now here they say we've got OB is 15I, so that's a starting point. We need to know the position vector where they meet, which is another sort of distance or point from the origin, right? Displacement. So when I draw this diagram, I'm going to be drawing my length units. So we've got VA is going 3 and 4 down. So 3 across, oh, that's not great. 3 across and 4 down. So we know it's going in this direction. I can draw it as long as I want because this is a velocity in the space that I'm drawing is just distance, right? So I'm just going to draw it on this angle. We know we've got our OB is somewhere out here. Okay, so origin, this is point B, which is 15, 0. This is my velocity A, which is 3, negative 4 in that direction. We know at some point they meet, and they meet at right angles. So let me just continue this line out. Right, they meet somewhere on this line at right angles. Oops, I'll draw an arrow for this one. So that's a right angle there, roughly. So B is traveling towards this particle A. They're going to meet at this point here, which is point P. And we want to know what vector OP is. So we're after this vector. Now, hopefully this looks familiar to you, right? We've done quite a few problems like this. This is a vector projection problem. We're after the length of this black vector, okay? Or we're after the actual vector, right? So let's label this to something a bit nicer. Let's call this B vector. We can call this our A vector. We're looking for the projection of B on A, the vector projection of B on A. So that's going to be A dot B on A dot A by A. So that's my vector projection of B on A. I can work that out. So we've got A dot B, we've got 3, negative 4. So we got 45 on 9 plus 16. So 5 is common to both, so we got 9 on 5, 3, negative 4. Okay, so that's my vector, my black vector here. So we know that the projection of B on A, 9 on 5, 3, negative 4. Now, the reason why we could use this VA here is because that's the direction that it's pointing in. It doesn't matter how long this vector is, this red vector, right? It could be this short. It could be super long. It doesn't matter how long that vector is. It just matters the direction that it's pointing in for when we're calculating this, because we need this to be at right angles. So all that matters is the direction of this vector. If we changed our VA, it wouldn't matter. We would still get the same black vector, and you could, the same vector projection of B on A. And you could do that at home if you wanted to. So we found that black vector. The position vector OP where they meet. So they're meeting at this point, which is this here. Okay, so that's their meeting spot. Part B, we need the velocity of the second particle. So we know that velocity equals displacement over time. This diagram is a diagram of our displacement. So we're looking at this blue vector. We're looking at the velocity of that blue vector. So, such that we know that they're meeting at point P, okay? So, the velocity of A is going 3, negative 4, and that's going to meet at this point with vector B. So, if we want to know the displacement of B, that's just going here and here. So it's going negative OB plus OP. So that is our displacement. We can work that out. Negative OB is just negative 15, 0, plus OP, we know OP, it's this. Down here is our OP. So that's going to give us our displacement. So let's work out our displacement. We've got 9 on 5 times 3. And then we're minusing 15. So we get negative 9.6. And then we've got 9 on 5 times negative 4. And then we're adding or subtracting 0, so we get negative 7.2. Okay, so that's that blue vector here. That's this vector is negative 9.6, negative 7.2. We need to work out the time that they're meeting. Okay, so are we? No, we need to work out the velocity. We've got the displacement, we've got that already. We need to work out the time of the meeting. So to work out that, we know for this one, we know how fast it's going, we know the displacement that it's going, so we can work out the time. V equals the displacement, the time. So time, so our velocity is 3 negative 4 equals 9 on 5, 3 negative 4, yep, times 1 on t. For both of these to equal, we know that 9 on 5 times 1 on t must equal 1. For the right hand side and the left hand side to equal, we get 9 equal 5t, t equals 9 on 5. So that's how many seconds until the two particles meet. We can then substitute that in to this. We know our displacement of our B. That's over here. We know our time is 9 on 5 seconds, so we can work out this guy. So velocity of B is displacement of B on time, which is negative 9.6. What was our time? 9 on 5, so 5 on 9, let's put a negative there, 9.6, 7.2. And that's our velocity of B. Okay, so that's question 3. I hope you enjoyed the video. I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.